Don't be lasagna. Well, who wouldn't be? Who wouldn't want to be? Eric would certainly want to have me be lasagna, so I don't know, maybe it's cool to be lasagna. You'd have to ask your favorite doctor again, so see this as your Doctor Who quote of the day. And welcome to Dirtling, where we build things. Bit of housekeeping first, in case you're watching this after the fact. Join the stream. Please join the stream. I'd rather have you here, have a bit of a discussion as well. You can usually meet us on Saturdays, 7 or 8 p.m. depending on how well the weather is, because I do have a dog. You can see him be somewhat nervous here because he notices me being nervous. 7 or 8 p.m. European time or Central Europe time, 6 to 7-ish UK, 1 to 2-ish East Coast, or 9 to 10 West Coast, 9 to 10 a.m. that is. So for all of you early birds, that might work out. If you're like me, you're probably still snoozing around that time on a weekend. So yeah, no choice, but sure. Meet us. Also, if you see something you like in the stream, give us a like, share it, comment if you think I'm doing something wrong, I'm saying something wrong. Yeah, let me know what you think in general. Let me know what you think, and yeah, let's get into it. So the task for today is we want to mod our Voron v0.2 that we built from a Fysetc kit. With a bit of luck, you can see at least part of it here. I may need to fix the lighting there. And this is a completely stock build printer. You saw the printer cam just now. We'll still need the printer itself for a moment before we can disassemble it. But one of the things we want to do is we want to exchange the electronics. To be able to do that, I want to do this step by step. So we first want to give this printer a CANBus toolhead board, because I think CAN is the better technology. It's the more compact technology. Also, it gives us more flexibility. One of my gripes with the R1, at least, not the R1.1, which was released by Fysetc in March, but the R1s have no way of selecting a different fan voltage for the parts fans versus the hot end fan. And I have fans that require this, so I'd like to use those. I already noticed the Fysetc provided fans making different noises than they did in the beginning, making some sickly noises. So those seem to already be deteriorating, which makes me think we should do this rather soon. The second point then being that we also want to later exchange the mainboard for potentially a BigTreeTech Manta M4P, because I like the way the Raspberry Pi CM4 modules integrate with those. They're I think the currently best boards on the market. There's also the Leviathan from LDO, also a pretty good contender, but I think for a V0 it is quite a bit overkill. So we're gonna go with an MP4 M4P. That's not today's task though, because today we are going to disassemble and rewire and reassemble the hot end. And I'm hoping we also get into the configuration part where we then need to deal with bootloaders and everything else. So before we can start though, I realized that I forgot to print something. That's what we're going to do first, because if you are going to do this mod, you will need a piece of, you basically need to exchange this, your cover for this piece. We're going to print that. Well, actually, let me think here. No, we're actually not going to print that, because I think it's going to be a bit of a problem with the connector for the Catalyst board. So we're going to try, no, we're going to print this, but we're going to try to make it work without this first, because this piece may be interfering with the hot end connector or the toolhead connector on the Fysetc Catalyst board. So that's the first task here. That's the first thing we need to do here, is just go into our slicer. Is that running? Yeah, that's running. Load that. Check our settings. Those are PIF settings. Let's slice it and upload and print. Filtering is already running, so we're good on that end. We have enough windows open. The one thing I would want to do is, well, actually it doesn't matter that much. We're likely not going to watch this printer do its thing. We are going to go into details about CANBus in the meantime, and how we are going to set this up. So a bit of theory first, bit of explanation first on what's going to happen here, and then we're going to go into more details afterwards. Once that print is done. Yeah, I also just realized that we may have another problem with the power distribution, because the power brick inside the printer is, so let's maybe get into this. We already kicked off the print. We can check that out. We can see if that's already doing something. Yeah, that's saying it is. Currently heating the bed. So I guess we can just jump here and give you a bit of a, well, actually, yeah. let's give you a bit of a better look. And yes, I am using a whiteboard. There we go. There we go. That should do. So there are two factors to this while our printer is printing that we need to go into, that I want you to understand the theory. The first one is wiring and control of CANBus, and the second part is about how your CANBus and basically any other firmware is working on a Klipper side, because I don't think people realize what's going on there to an extent that helps them understand what they need to do. To that end, let's look at the wiring as it is at the moment. We have a, let's say this is our power brick. That's the, what is it, LRS 150. That's inside our printer. I'm also going to turn off that light so you can see a bit more. So LRS 150. There we go. So that's our power brick. We have a plus, we have another plus, and we have, let's use blue here, 2 minus. That's our power supply. We have a catalyst board. That is taking up one of those pluses and one of those minuses on 24 volt. Yeah, let's do this there. Now we also at the moment have a Nevermore, and a challenge with this Nevermore was that we have two 12 volt fans in that. So what happens here is we get another 24 volts out here, and obviously also a ground, and those go into a buck converter that converts these 24 volts down to 12. And obviously we also have a ground connection there, so that works. Now those are all our connections that we currently have in our printer that uses up all the connections on the LRS 150. The problem is if we now want to include a CAN toolhead from an electrical perspective, we would need to also connect them to our LRS 150. I don't think I can recommend doubling up here. And what we could also do, something that I might end up doing, but I'm not a big fan of. Ooh, the printer just started. Let's have a look while I look for the Catalyst documentation. And show you what I mean here. Oh, that's the wrong one. Yeah, that's the right one. Oh, right, we don't even have that option. Okay, never mind. So, by the way, I'm a bit surprised that that printer is standing still here. Let me quickly check that. Now that should be fine. That should actually be fine. It is currently heating up. Anyways, back to our graphics. So what we now need to do is we need to more or less double up on this either of these connections here. I wouldn't want to use the buck converter. So what we will do is I'm going to move our toolhead to let's copy paste this, and then we are going to move our toolhead here. And what we are going to do is we are going to split this off. And we're going to split this off and connect it that way. By the way, the printer is printing. And let me quickly get you, oh no, I'm not going to bother. I'm going to monitor this myself. Should be fine. Anyways, this is how we're going to connect it electrically. Now, signal-wise, we are going to have CAN low and CAN high, and CAN low and CAN high. Need to then connect to our Catalyst board. That basically deals with all the connections we need to make this work. One thought I had was to potentially be able to source these 24 volt here from the current Catalyst connector. I don't like that much though. I don't like that all that much. So we're going to refrain from doing so. And by the way, I'm a bit anxious about the print still. The first layer looks a bit weird. I'm guessing because this is the first print we're doing on this today. This might not turn out all that well, but we'll see. We will see. Should be fine. Yeah. And I just realized I also have the audio enabled. That's off. Okay. That should be off as well. So there we go. That should be better. Anyways, so these are the connections we need. These are the connections we need to provide in some way. There is a connector for CANBus on the Catalyst board designated. So if we look at the connectors on our browser, weird, that's the wrong browser window. Let me quickly fix that. So there. We can see that there is a CAN-L and CAN-H connector right in the top left corner. It also provides a ground, but we're not interested in that. We're not going to use that. We're going to get ground from our power setup. So that's the basic connection. Now, from a virtual connection on how our printer will connect to this on a logical level, that's also worth discussing, is we're going to have our Raspberry Pi, and the Raspberry Pi will have a USB connection to our, let's use that again, Catalyst. Our Catalyst board will then, besides being a controller, act as a CANBus network interface card. So if you've ever connected an Ethernet card via USB to your laptop, for example, it's the same concept. But instead of being an interface card for Ethernet, it's going to be an interface card for CANBus. So this is going to be a CAN NIC, and that's, by the way, why Linux, for example, when you go and do your CANBus configuration on your Raspberry Pi, right? You're dealing with Linux networking. This is why Linux treats this as a network card, because it is effectively a network interface, and the concepts that apply to you connecting an Ethernet card do apply to you connecting a CANBus card or a CANBus adapter just as well. It's the same thing essentially. The difference is that your CANBus will work with not IP addresses, but CAN IDs to address the different computers, and there are restrictions, but it's just a different form of a network. It's just a form of network that you're maybe not as used to. But as soon as you understand, hey, this is just another type of, like, similar to Ethernet on a conceptual level, on a conceptual connection level, that should be fine. Now, the Catalyst board itself will not be controlled by CAN, or does not have to be controlled by CAN. It can just as well run as a non-CAN device, as a USB device, but you could also set it up to be a CAN device on its own network. Both are possible, and I think we're going to try both. The other thing we need here is our toolhead board. And the toolhead board obviously gets connected via CANBus. So that's the logical connection, right? And I did two here, but let's keep it simple. Let's not do two connections there. Let's just do the one. So that's our CAN network. If you had a second toolhead board, you could also go and run that directly from here. And by the way, that's even possible with the Catalyst board. It works just the same way. The only thing you need to ensure is that your electrical connections are then safe, are then good to be used. Speaking of, there are two main factors to consider for CAN. That's physical and logical connections. The physical connections are, for CAN in general, I think you can have about 40 meters of a cable, or 40 meters of bus length in total for your communication. Not relevant for 3D printing. The more interesting part is that if you have, and I'm gonna use the same colors here, if you have a CANBus connection electrically, and you have, for example, let's say there's our there are two devices on it. Then let's say this is the Catalyst and this is the Toolhead. Then these can be up to 40 meters apart in total. What you need to do though is you need to have a resistor at the end that's 120 ohms. And the same thing ideally on the other end to terminate those lines. Because what happens if you don't terminate those lines, if you don't terminate them together, is that you get something called signal reflection, where a signal would hit the end of a cable, and that end for that signal is roughly akin to a mirror. So the signal goes all the way to the end and then gets bounced back, and because it needs some time to travel from A to B here, and if you have another signal that gets reflected from the end first, you get interference. You get an unclean signal. That's obviously not what we want to do, what we want to have. So I think the Catalyst board has the ability to terminate the connection. We'll need to look at that. But I know that the SHT36 definitely will. It definitely can do it. So that's what we're going to focus on, I think. And this is what we need to go into next. We can actually get away with only one terminator in this case. Potentially. We'll need to see. It's not proper, it can cause problems, but we may get away with it. The other thing that I want to mention here is that these connections, this connection length can be up to 2 meters. So for purposes of a 3D printer, you can actually go and have, let's say, your controller and have your CAN cables directly split after the controller. Let's assume you have really short cables here, and then you have 1, 2, 3, 3. And you can have a can hub here. Well, now I would like to have an undo function. But this hub essentially does nothing else than directly connect these together, and nothing else than connect these together. Nothing more is going on. That's all. So this CAN hub can actually be a set of 2 Wago mounts. That works just fine. It works just fine. This can also help you in case you want to, for example, connect your ERCF and a CAN toolhead board. You just hook them up to the same cables and that's it. That's it. There is nothing to this. The only thing you need to make sure of is that you use CAN low and CAN high in the correct places, and that's it. So, and like I said, this CAN hub can be really close to your controller board even, because you can have these connections be up to 2 meters long. And if you're not building a Voron Phoenix, I think you're gonna be fine with that. I think that it might just be enough, roughly, potentially. Even if you want to connect your ERCF, the longer you make those, the more important it is to make sure that you use the longest one for termination. So if you have a, let's say you have a toolhead and you have a ERCF, then I would terminate on the toolhead and the other side on the ERCF, for example. So that's physical and logical layout. Again, we're going from USB to a CAN network. So just a different kind of network, but it's still the same general concept. Now that's the part for the connections we need to talk about. The other part we need to talk about is the whole bootloader shebang and what that means. You know that when you do a CANBus install or any install off Klipper anywhere, it gives you an option to leave space for bootloaders. It gives you an option to like just offset your program by a certain amount. Now the question is, what is a bootloader? Because I think it's important to understand what that is to get a good idea of what's going on here. For that, we need to look at how your firmware is actually starting up. And let's assume this is the, I'm going to move this a bit here, so there. This is your MCU flash. Your MCU flash starts at address 0 and ends at some higher, like let's say if you had 1 megabit of or megabyte of RAM, that's 32-bit addressable, you have 264 50, damn it, 256 K addresses, which means that you 0x3 F. Well, let's clean that up from a is probably your end address, right? So your whole memory, your whole flash memory is segmented in this way. It contains the program you're trying to run. If you, and this is in theory, the different MCUs, different microcontrollers may have different offsets that they require you to have. Some have bootloader control support built into. That's also a consideration, but we're talking about the basic concept here. So if you were to just want to run a program on your microcontroller, you write that to address 0, and your microcontroller, or the startup address, it might not be 0, but for simplicity's sake, let's assume it is. You write your program starting from 0, and your microcontroller will basically execute it. Simple concept, right? It can then jump around. There are different concepts where your microcontroller will need to jump around in the code from A to B, but it will always start from that 0 address to run. The downside to this is that if you don't have something that on boot is able to load a new program, so a boot loader, then essentially to reprogram your microcontroller, you will always need to use the manufacturer tools. You can do it, but you will always need to use the manufacturer supplied tools, which in some cases aren't available for Linux. So you need a Windows PC, you need Expressive, you need the STM tools or anything else to directly flash your microcontroller. Depending on what microcontroller you have, what manufacturer, there's a couple of different tool sets to use. Now, if you have if you don't want that, you can use something called a bootloader. And a bootloader is a small program that sits in the very beginning here. Right, so now your memory is segmented between this little bootloader thing and your actual program. And when your microcontroller, your Klipper microcontroller starts, right? That's the thing that actually executes Klipper. It will not immediately start Klipper and the Klipper service. No, it will actually start the bootloader first, and the bootloader will initialize USB and will wait on USB for a certain amount of time, or in general, well, in most cases for a certain amount of time, for a signal from the host computer, in this case the Raspberry Pi, to get a signal that says, hey, we want to upload something new. And if that signal comes, if the host computer says we want to rewrite this, then the bootloader will write from an offset address. And this depends on the firmware on the bootloader and how that's structured, right? Will write this memory. And once it's done, it will then have a jump instruction that starts this. And the bootloader on the actual microcontroller takes care of writing this. It's usually a DFU bootloader. So that's a more or less standard interface that you can connect to, that different microcontrollers support, and you just send the binary file to your bootloader. Your bootloader is able to write this. If the signal doesn't come, it will just jump to the startup address. So your bootloader, really, really practical thing. Now here's the kicker. This, in Klipper terms, is formally CANBus, nowadays Catapult. And yes, they were right to rename this, because CANBus was a bootloader that was able to receive a new firmware image via CANBus, which is the only connection we have to our toolhead board here. If you see that, right? The toolhead board is not connected to our Catalyst board in any other way. So the CAN connection is the only way we could potentially flash a firmware to that board once we have it completely connected, once it's in the system. If we don't have CANBus as a bootloader, we will not be able to flash our firmware on our toolhead board inside the system. We would basically need to take the toolhead, connect a USB cable to it, connect it to another Raspberry Pi or the Catalyst board inside that printer. It's messy. You'd need to have a USB port to begin with, which we don't have. So not ideal. So, but even if you have only use USB and a single mainboard, or USB to connect to your toolhead board, your mainboard still will have a bootloader, and it's probably going to be CANBus anyways. There are other bootloaders you can use, but CANBus or Catapult is what's used nowadays on Klipper. Now, I said this would be the only way to flash the firmware on our toolhead board. That means, and this is actually correct, we will not just have MCU main memory. We will have the Catalyst MCU will have a bootloader installed, and then a section of code that executes its firmware, but it also needs to communicate with our toolhead, and our toolhead will have the same setup. It needs its own bootloader and its own firmware to run. That's the difference between the setup of a single MCU and using a separate toolhead board with CANBus. Is both now become separate computers in this network, in this CANBus network. And they both need firmware, they both need a bootloader, and both need to be set up correctly. So what we will need to do at the very least is compile and install CANBus twice, and compile and install, or Catapult, let's call it Catapult, and compile and install Klipper twice with the corresponding settings for the MCUs that are used on those boards. And that's something we need to figure out. We will need to look for what the bootloader offset is. We will need to configure that correctly. We will need to look up the pins that we need to configure. All those good things. Yeah, so that's basically what we need to do to make this work. Now, most of this will come down to configuration, and I'm hoping we can find this stuff reasonably quickly, because I haven't necessarily prepared anything here. There's maybe one thing we can pull from the Trident. I have a couple of scripts that do this a bit, or let you manage this a bit better than Klipper itself does. But in general, this is what we need to do. So steps are, first of all, sort out electrical. We're likely going to use Wago mounts for the 24 volt side. I'll need to check whether they actually have a sufficient current rating, but in general it should be fine. We're going to use a JST connector, I think it is, on the Catapult board to connect our CANBus. It's going to be a bit tricky seeing which ones can high, can low. We have this on the toolhead, on the Catalyst board documentation, but we also will need to check this on the toolhead. For cabling, and maybe let's go into that, we are going to use these from BigTreeTech. These are my go-to for CANBus wiring. They have pretty decent, I think 16 or 18, no, I think this is 18 gauge wire. You do want to cut the ends here because they're pre-soldered and you don't want the solder there. They also have a JST connector pre-crimped, but the problem with this will be that it is extremely long and we're likely not going to need that, so we will need to take this apart. We will need to remove considerable length from this. Yeah. The other good thing about these is that the cable inside it is pre-twisted, so you don't need to deal with that yourself as well. It's just self-contained, and that's why I like them. That's, by the way, also why we are using a Mellow Fly SHT board and not a BigTreeTech BTT36, because of this connector. You can definitely do it with the BTT36, and you'd need to use the Molex connector, but I like these XT30s better. So that is the reason, and by the way, the only reason why we are preferring the SHT36. From a conceptual point of view, this should be just the same. There's no difference whatsoever conceptually between those boards. Should be fine. Should be completely fine. Yeah, that's more or less what we're looking at right now. Using this board, using our nice little cable here. I'm hoping that this cable will fit through or along the current cover, so we can leave the cover in place. But if you're interested, and let me see if I can now, I still need to check the battery status of our microphone here, and I am going to switch to the second connector here. Turn the other one off so it can still load some more. There we go. And now I am actually free to move. All right, okay. So let's check the printer. You can see it's done. And yes, we will use this once we move the mainboard to whoa, nice. We will use this at the very latest once we move the mainboard to the Manta MP4, M4P. But we'll need to see. Squish on this, by the way, way too far down. So we got an insane amount of elephant's foot. It looks like this printer definitely needs to preheat as well. And there may be something said about adjusting Z. I'm not quite sure why it would go up though. But no matter. Like it's like with every single 3D print. It doesn't necessarily need to be perfect. You can, and in most cases will always have to do, or in most cases will have to do something to that print afterwards, so it then actually looks good. The nice thing is that we have a very well squished, very well squished bottom with a nice texture. So that's pretty good. Yeah. Okay, so I'm not sure if anybody's here now. I haven't checked the participants, but if you're here, if you're interested in having a conversation, if you're interested in chatting, asking questions, feel free. If you're not here right now, if you're not watching live, but you do still have questions or you do have remarks that you want to let me know, there is a comment section. You can leave me comments. The video will also, well, yeah, just put it in the comments. And while you're down there, or while you're typing your responses, your whatever you want to tell me, leave me a like if you find this useful. And yes, I'm getting sidetracked here a bit with cleaning up this print. I just want to have it out of the way. If I need it, it needs to be there. It needs to be reasonably well. Worth it. Okay, and that should take care of the hole for the. Okay, nice. See, that is how quick you can clean up a 3D print, especially with a huge elephant's foot like this. I'll have to investigate that separately, where that's coming from. Maybe a setting or something wasn't applied correctly. Who knows? Who knows? Yeah, otherwise, if you enjoyed this theoretical discourse into CANBus and you're watching after the live stream, then maybe try joining one. Maybe come by, geek out with us, have some fun. Yeah. You can find us Saturdays, usually Saturdays. Last week we did a Sunday stream. 7 or 8 depending on the weather. I usually start either on either of those times, but it kind of depends on how long I will stay out with Enik. Yeah, 7 or 8 on Saturdays European time. That's 6 to 7 UK. 1 or 2 East Coast, or 9 to 10 West Coast. Just come by, have fun. Let's geek out. By the way, in case you're interested, what's in the box for the Mellows Fly SHT? This one is the one with support for the max driver chip for the PT100, PT1000. It's about 36-ish bucks, so it is considerably more expensive than the EBB36. So if you're not like me and you really want the XT30 connector, then just go with the EBB36. No problems whatsoever. In the box is a board in an anti-static bag. We have a USB cable. We have connectors to crimp and a heatsink. That is only one heatsink, not two. And from the looks of it, we can see that in a second. From the looks of it, this heatsink, oh yeah, it does fit. So what we're going to do, because these boards tend to run hot, and that goes for all of them, that's not only the EBB36, but that also goes for the SHT36 and probably any other controller board, the LDO Nighthawk as well. By the way, crimp connectors, pretty good, pretty decent amount. Because that's the case, we are also going to apply a heatsink to the actual MCU. It's just good practice. The other nice thing about the SHT36 that you should consider if you're not interested in the longer cable and the self-contained cable, that you have to buy, by the way, separately from BigTreeTech. So these are bought separately. They're another $5 to $10, I think. Don't remember exactly. The SHT36 comes with a cable. So get that. They actually give you a cable with this nice connector. It's a really light cable. It's a really flexible cable. So that's pretty decent. The only reason why I really don't use this is because it's not sheathed. I like the sheath version that BigTreeTech builds better. And I'm kind of, by the way, this is about as much cable as we will really need. If you remember the V0, this is really floppy, this is really flexible, so we're likely going to tack that onto the PTFE tube to give it a bit of stability. And or we also have piano wire to keep it up. So we'll need to see how that goes. There are a couple of things we can do. But in general, pretty good, pretty decent. I think that's going to be a winner. And it is definitely more flexible than the cable we get with our Fysetc kit. Anyways, I'm going to put the SHT packaging out of the way. I'm going to move the cable. Keep this in mind. Keep this in mind. I'll recap it in a second, but in general, this is the stuff we need to account for. Remember, physical connections. We need to make sure that we get Wago mounts to connect our power for the tool head. We need to connect the LAN of the Catalyst board. And I think I will actually build one of my funky little 5-way CAN hubs that I also have in the Trident. As an interim solution, or, well, should I actually show? The question is, do I really want to show you this stuff? Because it's a bit hacky, but CAN switching isn't really, or CAN hubs really aren't any big deal. Cool. Yeah, so keep that in mind. We will first deal with the electrical connections. We will need to disassemble the tool head and like remove the wiring there, connect the Catalyst board, and then rebuild the tool head. we're going to exchange those fans, or the fan, I should say, because it's only one fan that we actually have a problem with. We'll need to see how we need to configure that on the SHT36. And then we get to set up Klipper. We get to set up and compile Klipper and the CANBus or Catapult bootloader, get to install the CANBus bootloader and Klipper on the main MCU, and then Catapult or CANBus and the Klipper firmware on the toolhead board. And once all of that is done, we have figured out all the IDs, then we're good to go. Then we're good to print again. And hopefully with a nice, reliable setup. What we also probably going to do is we are going to do the LEDs for the toolhead at the same time, because that's one of the other reasons why we're doing this, is because this has support for LEDs on the toolhead. That's something you do not get with the R1 v0 kit from Fysetc. Okay, enough said. That's the theory. I will not remove this. I will keep it as is so we can pull it out whenever we need to talk about it. And now it's time to take apart the printer. It's actually, to be very, very honest, I am actually hesitant to do so, because this printer has been doing a really reliable job. It has been working really well. So some would question, why even do this? Well, first of all, because we can, because I want to, because I wanted to, let's light this up again. Wanted to show you how this is done. This needs to be done, and I'm an idiot. But also, because from a data security point of view, I need to do it. I need to exchange the electronics, and I need to do it step by step. Nothing I can do there. Nothing I can do there. By the way, as long as we're waiting here. By the way, printer. The printer. This is it. I don't think you've seen this in its full glory for some time now. It looks really, really good. And this brings me to another set of amendments as well. The reason why I need to do this, the reason why I need to exchange the electronics, is because there are serious concerns from my end about the security and future security of the Fysetc Catalyst boards. Not because I think Fysetc is in any way malicious, that is bullshit. I think they're enthusiasts just as much as anybody else. Yes, they're trying to make an honest living with this. Yes, they provide really, really cheap kits that you can build decent printers off, especially if you want a build and you don't mind not having the most precision, for whatever that's worth, components. The problem I have here is that this printer is running on my on a network that, or is supposed to at some point run on a network I use for professional work. And with that professional work come strict requirements for the security of devices I connect here. So if I build a system myself and I know what's going on there, I can consider that secure. But if you have a device running on your network that is supplied with a Chinese operating system in any way, and by the way, none of the manufacturers are actually malicious, but they are all required to supply the Chinese Communist Party with any information they have or can acquire and support the Chinese Communist Party in any way. So even if there is no malware in the current distribution of the Catalyst board firmware or the Linux operating system that is included, if push comes to shove, they would be required to add one. If the CCP asked for it, they would need to add one. And then you need to remember that you are getting automated updates, and you're getting automated updates from Fysetc and not from Klipper itself. So in theory, whenever you get those updates, Fysetc would have the opportunity to install malware after the fact. Now, one user, Maker Milo, thanks for reminding me on that, mentioned that you can actually create your own Linux distribution based on the Rockchip SDKs and the operating system that Fysetc used to modify this. There's one problem with that for me personally, and please remember I have a corporate interest here, not just a personal one, and that's usually what the CCP is interested in if they require information support from a company. Rockchip and that Rockchip distribution are also Chinese products. Yes, the packages are not, but the Rockchip distribution is, as far as I know, and please correct me here if I'm wrong, because I would be so happy if I were, a Chinese product. And it being a Chinese product creates this dynamic of me not being able to trust Rockchip devices as a whole. Is the basic sentiment here. And let's look that up. Yes, just check that. Fuzhou, China. So even if you were to build the operating system, like even if you were to use the standard operating system that exists for those Rockchip chips, that's heavily modified by the Rockchip developers, and it's not that you couldn't build one that you can trust. I'm not saying that's impossible. The reason why I am going to use a Raspberry Pi and a completely open source Raspbian is specifically because I do not want to make the effort of creating a completely custom image that uses the software and bootloader that or a software and bootloader that has Rockchip support but doesn't come from Rockchip or a Chinese vendor and isn't closed source, and then build my more or less custom own operating system on that. I could certainly do that. The problem I have with that is it's not worth my time. It is much easier for me to just put in a Manta M4P, put a Raspberry Pi CM4 on that, use an image built from an open source distribution that has seen many thousands of developers, even, I don't know, could be millions or hundreds of thousands or tens of thousands, I don't know the numbers, but many people have looked over those, and those I can actually trust. That's important, right? And for those, I also know that I get security updates for them regularly. So once I move to a Raspberry Pi and Raspberry Pi OS or Raspbian, that's something I can personally trust without having to go through all this hassle to make that work in the first place. So that's the basic reasoning. It doesn't mean that you ultimately have to jump and fix that for yourself. It just means that I will not bother. Now I think our printer is almost at temperature. The reason why I, by the way, reconnected this is because I forgot to take out the filament, and we will need to do so because we will potentially also need to modify the filament path, and we want to play with the tool head, so we want to disconnect the PTFE tube. So just good practice to take out the filament. We'll need to retract that a bunch of times. Oh, come on, just a couple more degrees. Yeah, but that's the amendment I have to make on what I said about the operating system and me not trusting it. Again, it might be completely different for you, and if you say you don't care, or if you put the printer on a separate network, no big deal. But keep in mind that if you have a vested, if the CCP has a vested interest in the data that's on any network that you connect to your printer, they could potentially, if they can find out that you're using Fysetc kit, or if they just blanket do it, they could require Fysetc to include a kit, a rootkit that would then be able to connect to the internet easily, because it would connect to the internet basically the same way as your automated, as your updates, as your auto updates, or your firmware updates in general. So there's literally, it's really not easy to detect those. Yeah, makes it all harder. So having a system there that I can trust is really important to me. And I think I said this before, the same thing in my personal case goes for any printer by Bamboo, by Creality, by anybody else. Not necessarily, well, I'm especially weary of companies from China because of that law that forces them to help the CCP in any way. But obviously there are other concerns here as well. Bamboo is not a Chinese company, but they could still have security issues on their network, on their connections. They could just as well get hacked and have some kind of malicious software shipped to you during your updates. But to be fair, that could happen to Raspberry Pi OS and those repositories as well. But it's something to keep in mind. It's something to keep in mind. Make sure you can trust your network, and make sure that you protect your data. Separate your printers and your printer network from your personal data, from your email. Because remember, these are computers. And these computers can, if they have automated updates enabled, it is immensely easy for somebody who can control those automated updates on the server side where you're getting those from to also install something and run something that they don't need to connect to from their end to control the printer. They can just have the printer connect to them, and that's the same connection that's going to be used for your auto update, so there will be nothing in the way. Anyways, ranting here. I think the printer's up to temperature, so let's retract this a couple of times. Let's get the filament out. Some good news as well, and thanks for pointing that out to Maker Milo as well. Go check that out, check out his channel. He built a really cool printer from the R1.1 kit. It was supported by BigTreeTech in actually setting that up. It looks really nice. It looks insanely nice. Good job. Yeah. Let's shut this down. All right. Our clipper is down. And now we can turn it off. And yes, try to shut down your printers from the mainsail or fluid or whatever else you're using side first before you go and try to shut it down via a power button. I know most of the time nothing happens, but if you ever had a corrupted file system, you know that's no fun. That is no fun at all. You're going to lose data. It just sucks. Okay. We have a printed part here. We need space. We need space. Here we go. We are going to take off the door because the door is going to flop around in the breeze and we don't want that. And once the door is off, we are also going to need to open up our and yes, contrary to what I said, I again forgot to loosen the hinge on the bottom first. So try to do that. Bottom hinge first, then the top one. Might work out better for you. We can also actually go to the top cam, zoom that out, and adjust this a bit. Yeah, it should be fine. I will show you in a second why you should do that. If you look at our hinge here, let's see if we can actually capture that. You will hopefully see that it is cracked. So that kind of sucks. Especially since that is a part where we also applied VHB to, so I was kind of hoping that would last a bit longer. But yeah, that already cracked. That sucks. Going to put that aside. Then we need our nice multi-tool. And by the way, yes, you will notice that I haven't actually mounted the tools on the side here. Too many things going on. Too many things going on. You may have seen it in the background, but I kind of got sucked into the whole PC handheld scene somewhat, and I am very much enjoying myself playing things like Forza and other stuff on the Lenovo Legion Go at the moment. It's really fun, and yeah, I enjoy it a lot. So that takes some of the time, and then you know how it is. I obviously don't spend as much time on other things. Anyways, let's disconnect this and let's take out our screws here. And I'm tempted to also put in the CNC'd extrusion here. We'll see how it goes. So we'll see how it goes. Obviously there needs to be a working printer first. Although if we put in the CNC extrusion right now, we're likely to lose some stiffness in the whole contraption. So I'm not sure I want to go there. So if I can't decide on something, I usually go with pros and cons. The pros would be it's fun and it's something else to do. The con would be increased risk that we don't have a properly working printer at the end of the day. And by the way, I consider this a con to the point where I don't even expect us to have a working printer at the end of the day. Because with all the configuration work that needs to happen here, I'm not sure we can actually fit that into the, let's call it time allotted. Okay, so our tool head is off. I am just going to blatantly disconnect all the things here. We can likely not reuse much of those anyways. We'll need to recrimp our fans. We'll need to recrimp a bunch of things actually. And yes, I know people tend to rip these out. I'm actually very careful with these because Yeah. Ooh. By the way, yes, that harden is still warm. It's not hot, but if you're doing that, make sure not to burn yourself. Okay. Okay. So one left. That's the that's the main connector. And I think I have the bit flying around on the table already. So let's find that real quick. Oh. Yes, that looks good. So I'm kind of regretting not having cleaned up the and mounted the tools already. Because then we wouldn't have a mess. Removing the hot end connection here, pulling those out, and that's our Catalyst board free. That's the Catalyst board free here. The reason why I did it this way is because those Molex connectors are a pain in the ass, and rightly so. You don't want to have those coming loose, but actually getting those loose is not that easy, not that easy. Yeah. It is not that easy. So, next thing we want to do is we want to take off the Molex connector here. Well, actually, that seems to resist somewhat. So we might need more than one access location. So let's take our printer. Let's put it on its face. Being a bit careful not to drop it too fast, because at this very moment it is resting on its button, basically. I'm going to take these. Off as well. Move those down. And that's our electronics compartment open. Now, what do we do next? No, we actually can't read that well, but we may have a chance to get our I have a fantastic idea, because we need to reach that plate there anyways. Yeah, okay. And it likely makes a few things simpler. Let's take off the tool head, the head. Let's see if we can make that happen. Oh no, haha, haha. Okay, so issue being that there's a nut in here, preloaded, but there's a fixed heat set insert on the other end up here. So simply sliding that out is not going to work. We should still be able to slide out this back panel though. Yes, yes, that works. Cool, cool. And there we go, there's our printer. Going to screw those in again so they don't flop around in the breeze and potentially damage anything. Same goes for these. Just to make sure they stay in place. And are loaded in a way that they were meant to be loaded. So there, one simple test I want to do right now, just to see what happens, just to see if that would work, is see if the cable fits into this slot here. Yes, barely, but yes. So we can, for the moment, reuse this panel and just run the both the umbilical for CANBus as well as the filament through the same slot here. We don't need to move or do anything else funky with the with the cable or the plate there. That is very comforting, to be honest, very comforting, because that was one of my main concerns. Now we opened this up so we can get a better hold on the Molex connector, and I basically did it to get my finger under the Molex clip here, because that's in very tightly, so I can push and wiggle that, because that cable is not coming out otherwise. It is very much in there, and to be honest, I like it. I do like how stable, how sturdy that connection is. The only thing I don't like is this whole cable loom there. It's the... And yes, there is a neoprene sheath for it in the kit. I never mounted it. And yes, I should have. but we knew what we wanted to do, and having the sheath there wouldn't have made a lot of a difference. Whew. Nice. So it's out. It's out. There it is, the beast. There it is. That goes away, and obviously for the moment we do not need the printer. What I'm asking myself though is, where's sound coming from? There's sound coming from. Okay. Cool. So we're just going to move this aside for a moment, because first we obviously need to deal with the other side of this, with the toolhead. We need to rewire that, and once we have the toolhead rewired, then we can get into the actual printer again, do the electrical wiring there, do all the other stuff there. And it's nice to have a bit of space on the desk. It's actually, I'm very keen on seeing how we're going to make the NXK3 build work. That is going to be, it's basically 50% wider, 50% deeper, and I think more than 50% higher. So it's going to be a bit cramped. Going to be a bit cramped. Cool. So toolhead. We need our board. The board in good old NEMA 1436 millimeter fashion fits on here very well. The connectors are actually pH. Ooh, they are P. That is nice. That is nice. I thought I would have to recrimp those. Oh, that means we actually had we would have had the connectors. Okay, but let's not jump the gun here. Let's not jump the gun. Let's grab ourselves some jumpers and the documentation first, because that's the first thing we should do here, is get through the documentation and configure this board. We need to configure voltages for the 24 volt blowers for parts cooling, as well as the 5 volt radial fan for the hot end. We need to pop in said radial fan. We already have, well, actually, do we? I'm not 100% sure. Let me put up the decorations there. Okay. Oh, we also need these. There's our fan. There's one set of LEDs. The question is, where's the second set of LEDs? Where did you go? Where? Oh, where? There we go. That's the second set. This set, by the way, we can't use because, as you may be able to see here, there is a problem with the wiring, or rather with these tunnels and how they're set up, because there's at least one sharp edge in there that we need to go in and clean out. That's a bit of a hassle. But yeah, I just realized what a cool upgrade the SHT36 is to the Catalyst board, because it is using the same connectors. That is freaking amazing, really. I thought we'd have more of a problem there, or like more of a requirement for additional crimping. I mean, this means that even our hot and cooling fan has the correct connector already. How amazing is that? We will need to, because of the position of the hot and power connector, we will need to swap and because these cables are pretty short, we'll need to swap the heater from left to right. So that means that we will, at the very least for that, need to take off the cabling again. Which means we can also take out the hot end. And yes, I haven't exhaustively tested this fan, but as I said, there's already a worrying noise coming from it. I'm already at a point where I don't like to trust it anymore. So we're just gonna replace it. That goes in this way. And this goes in that way on top. There we go. We will already do the swap from left to right for the heater cartridge. We'll have a look at the other part. Yeah, that's fine. So that gives us options already. Now there is, by the way, one significant difference between the SHT36 and the toolhead board for the Fysetc toolhead that I just realized. This has one advantage, just in case we run into this issue. This is actually more stable because Fysetc is actively using the PCB to stabilize the toolhead board. They're doing this, by the way. Let me see if I can improve lighting here. There we go. They're doing this by way of having not just two screw holes that are defined by the motor, but they also have these two additional mounts here. So that's something I didn't realize before. The way that Vorons deal with that is using a backplate. Whoa. This specific backplate. So what we likely need to do here is add this backplate for the stability. And let me zoom out again. Well, actually, let's keep it zoomed in. Use the backplate for stability, and then mount the EBB36 on top of this, the SHT36 in this case. And I do see some problems with that approach. Huh. We could do it the other way around. No, I don't like any of those. Okay, so dear Internet, I was ill prepared for this. Please help me. Let's go to the internet. Let's find out how we need to do this. Our reference is this. So these will definitely not cut it. None of these will. Clockwork 2, Ponte, LHX. Neither of these will do it. Let's look at images. gonna do it. That might. Yeah, all right, that might do it. I like the fact that this actually includes zip ties for, or doesn't necessarily have to be zip ties. We're likely going to use Velcro instead. There's spacers for the board itself. All right, let's do it. Let's do it. We don't want to log in, but what we need to do is we need to print it. And now here's the most important dilemma I have at the moment. Our tool head is so yellow that I would actually like to get some turquoise in there, so we will need to load the other filament. Yeah. Let's enable the other printer. I'm so curious to see if that still works. And let me see. Okay, the filament is still in there. And we're just going to print that. This is why it's good to have a decent replacement printer. And with decent in case of my Voron Trident, I mean absolutely insanely amazing. That thing's a real trooper. We will need to do some changes to that though. Not next week, but the week after. I want to, at the very least, get into the electronics compartment and do a bit of cleanup there. We'll see, we'll see. Also, while that is booting, let's go 414. Let's get that printing. Four is up. The webcam is there. Oh, let me take you along here. So 4 is up. We want to heat that up to 250. Yeah, so preparation. Preparation is everything. Considering that we are already 2 hours in. Would have been the thing to do. Would have been the thing to do. All right. Yeah, there's a couple of things we actually need to do to the Trident, because for one, there are 2 filament sensors in the toolhead, one before and one after the extruder. after the extruder works fine. The before the extruder is cabled in a way that is a bit stupid. It basically always triggers. It always says that there's filament in there. So that's kind of useless. We need to change the wiring there. I was hoping, and that was the problem, was that the way I wired it would require the toolhead to, and let me actually disable the mobile cams in here, would actually require the printer or the toolhead to have support for pull down resistors instead of pull up. And if you're interested, those SB2240s do not have support for that. Just doesn't work. If it had, we wouldn't have a problem, but because of the pins I had available, I decided to wire them up in a bit of a stupid way, and that or in a bit of an experimental way, I would say, without checking, and that was the stupid thing to do. And yeah, that resulted in that one sensor not doing what it's supposed to, sadly. It's as simple as that. All right. The filament is out. Can move that over. Yeah, that's not going to be a good time. Yeah, make sure that you're always spooling your filament correctly. I just basically created the jam from hell just now and had to unspool and for some part respool this, because it would have resulted in the printer hanging otherwise. And that's no fun, and it will cost you more time than actually doing this, even if you do it multiple times. So that is fixed. And now let's get our turquoise ABS. Let's run off that print real quick. And with real quick, I mean, it is likely going to take the better part of an hour to do so, because even if the print itself just takes 20 minutes, the Trident for how good it is, has one serious drawback. It is damn slow on heat soaking sufficiently. There we go, that's that. Let's remove the filament. Oh, that's actually not a good location for you. Come here. And we obviously also need to turn on our filtration there. Filtration in the Trident, by the way, because we haven't properly hooked up the Nevermore, because it like the Nevermore I completely built there, but it isn't hooked up as it should be, because it's 12 volt and I can't connect the 12 volt fans to the currently 24 volt supply, so that's kind of a bummer, but well. Okay, so 19 minutes. What we're going to do now is we're going to just have that cool down, and then we're going to heat the bed to 110, because the startup script on this printer actually uses a dynamic algorithm or formula to determine how much preheating the printer needs to perform a consistent print. The base number for that being, I think, about 25 minutes. But if the print bed is already hotter, and it uses the print bed temperature for that, if that's already hotter, then it takes a bit of time off of that. So if you're printing one print after another, the additional soak time it will apply depends on how long it had time to cool down, and usually turns out to be 3 to 5 minutes. But if you just want to do a quick print, and by the way, if you do that, if you really run the beast as it should, perfect, works out well. But if you just want to make an itty bitty fiddly print like the one we're doing right now, not so much. Not as quick. The smaller prints don't necessarily rely on a well-soaked printer as much though. So with a bit of a trick of heating up the printer and to some extent the chamber as well first, we can actually get away with having a shorter soak time. The reason, by the way, why it's important to soak this printer and why it's... Oh shit. Oh, that is not good. The reason why it's important to soak this printer is for first layer adhesion. I had a couple of problems with prints coming off the bed if I don't do it, because the thermistor off The print bed is obviously on the bottom side in the center of the print bed, and there's only one. And that's the place where it's usually going to be hardest anyways. So you can imagine it's just not good. It's not reliable. You can't rely on everything and every place on that bed having the same temperature if you just let it soak for a while. If you don't just let it soak for a while. You need to distribute that heat. It needs to move to every single part of the printer. And only then do you actually get a consistent result. Okay. What we also want to do now, since we have some time, we can't actually mount our board. We want to configure it. So while our printer is printing the mount, we are going to go on the internet and we are going to find us the documentation to this board. The way I do this is I usually go through the Mellows website, which contains some of the information, or their GitHub. In this case, we're going through the GitHub. You can see here there's two versions of the Mellows SHT 36. You can identify those, I think, by the connector. And you can see here, this is actually the SHT 36 version 2. One of the major changes here is the connector. So the version 2 is actually what we want to look at. Version 1 was very much closer to the EBB36, with the connector being a 4-pin Molex. So yeah, we're pretty good off with this. We have the schematics here. This may become important if we need to figure out connections. But what we actually want right now, what we actually need right now, is a pin diagram. We need a pinout. So let's keep that tab where it is, but let's duplicate it and let's look for the description, for the help. And in case of the SHT36 Mark II, that's done via AliExpress. And we're gonna reject those. You can both use AliExpress directly, because Mellows, as well as many other of the Chinese vendors, and by the way, you can see it here, 18 bucks for, let's actually quickly look at what they have here. These are just the U2C modules. So what you really want and what you really need is one of these boards. You can see here there are two additional add-ons, I would say, that you need to look out for when buying these. One of those is also relevant for the EBB36. and that is the PT100, PT1000 controller. The other one here is the encoder. This is important. An encoder, I think, is meant to be used with a filament sensor, so you can actually measure the amount of filament that is being extruded. You don't need that. I wouldn't need that. I wouldn't worry about it. If you ever want to use either if you specifically definitely want to use a Goliath hotend, then you really need the PT100 sensor. That is a high temperature, higher accuracy thermistor that can actually go to 500 degrees Celsius, but that's not the reason why you need it for the Goliath. You need it because the Goliath hotend does include one of those sensors, and you can't just connect them to a normal sensor port. That doesn't work. So PT100, PT1000 support you need in case you actually want to run a Goliath. I'm not 100% sure, but I think the Rapido hotends come with the normal NTK, NTK 100 or something thermistor, the 100 kilo ohms thermistors that are very, very common. Those you don't need PT100 support for. If you're unsure, I would probably spend the $10 extra, but in general, most people, especially if you're building a Voron 0, you're going to be fine with the $26 version here. Just so you're aware, the encoder I don't think anybody will need. It's a nice gimmick. I still have to play around with it, but I don't think anybody will need that. Yeah. Now the way this works for Mellows specifically, and getting their documentation, I already said they do post extensive documentation right into the product description. But more importantly, they do have a separate page for catering to documentation requirements. And it's probably worth looking at that specifically. So they tell you a couple of things here. They do have CAN termination. They do show you the pinout here already. They show you a wiring diagram even with the plus and minus here, so it's pretty standard. So in general, I like the documentation of the BigTreeTech boards a bit more. Because while we do have the documentation here that we need to hook it up, we also need the documentation that we need for actually configuring Klipper, and that is only available on their support site. That's not available here. So I was kind of hoping that there was a link here somewhere. But I cannot for the life of me find it. I might have missed it further up. Yeah, but the important thing is we also need to get the ports and the configuration suggestions for this. And that's not here. Oh, let me, by the way, move this to English, because obviously you will want an English description to help out here to have a look at as well. Okay, so it looks like we're going to keep that. That's going to be useful. And we're going to duplicate that and yeah, fly clipper dogs. Okay, so this is the one we were looking for. We want this in English. So they have Google Translate integrated. It's going to be a bit of a Chinglish experience, but it is going to be fine. And there you can see the different mainboards they have. The reason, by the way, why I know my way around this is because I had to custom flash a one of their ERCF CAN boards, and yeah, that worked just fine. All the information was there, you just need to know where to look. There we go, that's the CANBus SHT 36 version 2. Interestingly enough, there's a version 3 on offer here, so I guess we're getting even more new toys. But we're good with this. We're good with this. You can see the features here again. The changes, we get the documentation, the pinout, wiring is here completely integrated. So yeah, it's pretty thorough. And there is the documentation for the fan. Now here's another conundrum. There's only one voltage selectable. That sucks. That is unfortunate. One interesting thing, though, by the way, is that you can see that here. We'll grab that later. Mellows actually supplies MOSFETs for fans on daughter boards, which is the part that's usually failing if you connect the fan wrong, or because if the fan fails, then it can take its MOSFET with it. And to enable you to just put in a new fan, you can also buy these MOSFETs from Mellows specifically and just replace them. Also, I need to sit down. Standing around really didn't do much. Let's move this up and let's see what we can find here. The BigTreeTech EBB36, by the way, should have separate selectable fan voltages. And being that I do want to use fans with different voltages for the hot end as well as the parts cooling, it makes me think that this might not be a good choice here. They also show us how to connect clicky. That's fine. Beacon supports in there. Let's look at the pinout. Let's look at the pinout, what we can hack here. So we have our temperature sensor, we have our harden, we have two fans supported here. Those two fans look like they need to have the same power. We have the CANBus termination there, and we have a switch that lets us decide between 3.3 volt and input voltage for a specific pin PA1, and that does not help us either. Okay, okay. That's kind of unfortunate. So I guess at the very least we need to now figure out how to hook everything up. Let me confirm something real quick here. I specifically need to look at the tool head for the salad fork. If you remember, I had that somewhat built up already. Yeah, there we go. Because it has an EBB36 on it. Interestingly enough, though, it also does not have the second fan port. So yeah, you can see it here. Thermistor fan 1, fan 2. So at the very least, both of these boards assume that we would be doubling up on the fans. Now, the one thing I would still want to look at here is how or where we select our fan voltage. But I don't even see enough. There's a bunch of jumpers here. Because the idea would be if the EBB36 can do what we need it to do easily, might be worth considering to move over to that. But since I didn't wire that up completely yet, let's look at the pinout. Let's look at the pinout. There we go. Oh. Oh. Okay, that sucks. That sucks hard. So, EBB36 I really cannot recommend. I really cannot recommend it because I am absolutely spoiled by their SB2240. Their SB2240 is an absolute breeze to work with. You have multiple fan ports. Each fan port has a separate voltage selector between 5, 12 and the input voltage, which can only be 24 volts sadly. So yeah, that's kind of a bummer. Yeah, it has so many more possibilities, but if I had to choose now, seeing what we saw just now about the configurability of the EBB36, I would definitely prefer the Mellow at least. Now this puts us in a bit of a bind, because that means that we now still have a discrepancy between the fan voltages. We are forced to use 24 volt for the parts cooling, so we can still not use our actually preferred fan. We still need to use the one from Fysetc. That kind of blows. But also, we now need to wire up a solution for our parts cooling fans to run together. I mean, it's not that it's hard or anything, but it's just a bother. It is just a bother. But all right. Well, we'll make it happen. Oh, that is the wrong way around. It needs to be this way. Needs to go in there. Put that into there, and then this cable in the channel, that in there. Okay, so I guess the Fysetc fan will get some more of a test before we can actually replace that. And replacing these will be a separate step, because it means that we will need to move to the 5 volt parts cooling fans from soon on to make that happen. I'm not sure if I'm going to do that anytime soon though. We'll see. Okay, so one of the fixes we wanted to do is out of the question. What we can do now, because our printer is actually soaking for way longer than it would have, and because our filtration, at least one of the two, I'm using these Anycubic filters, is charged sufficiently now, is we can start our print. Should have thought of that earlier. This whole investigation kind of threw me for a loop. Say what? Say what? No. He stopped that shit. Let's restart that. Let me show you what's going on. Our little printer just preheated the bed to 60 degrees instead of 110, which is caused by this being PLA. This needs to be Polymaker ASA. And now we need to slice it again. Going to take 18 minutes and a bit. Let's run that. See how fast this printer was back up? Yeah, that's now preheated at least somewhat decently. 38 degrees, it's fine. The position of the sensor is not ideal, so 38 is a good start at least. Okay, so what do we do here now? Well, first of all, we're gonna place the frickin' heatsink. While we place the heatsink, I can think about how I want to handle the rest of this fiasco. Okay, that is one heatsink on. Now let's see if we can find the others. Let's see here. We're just gonna leave that there, just in case we feel adventurous today. And by the way, it's reasonably important that you place the heatsink early, because it needs some time to settle, to harden the adhesive. And I love this Trident, seeing that Trident at work. It just does it. It's not the quietest printer, but it does what it's supposed to. Oh. Yeah, so I'm not sure where I put the heat sinks. Since this is going to be exposed and we can edit later. I'm not sure we actually have a problem here, or we need to do actually do something here. Right now we can leave it as is for the moment and then add the heatsink later. I will probably look for that off stream, and then we can just put it in once we feel it is necessary. Let's move back to the browser. So that basically means that we need to do something tricky with the plugs here. By the way, in situations like that, you can clearly see that I don't prepare these, I don't do anything off screen. You're seeing me work things out right on the spot. This may at times become somewhat boring. If you feel that way, please let me know. Put it in the comments, drop me a line in the chat if you're here. I'd really like to hear from you. Yeah, but this is how it goes. This is what to expect. Ooh, and that is really not done well. Damn, people. I'm seeing a bit of an issue with the assembly quality of this board. There's a connector at about a 5-degree angle. That is, yeah, that's really not in there. Damn. And by the way, you can see that it's the connector that's at the let me show you this real quick. Just for shits and giggles. So if you look there, see the connector all the way in the back here, where I'm pointing with the screwdriver. See how that's angled? If it was bent, you would have both pins on the same at the same height. But if the connector is actually soldered in crooked, then you get this angle of descent between the two pins, and you can clearly see that there. So that's kind of a bummer. Mellow, what the hell are you doing? I don't think that's a good thing. Also, let me move back to the thing, and let's run the air filtration. Oh, and let me check the initial layer here. All right, should be fine. Should be fine. No problems whatsoever. Cool. So, continuing on, making a plan here. Making a plan. Our expectation of having multiple voltages selectable on the board did not come true, so that kind of sucks. We could. That is something we can check here. We need to first let's close the EBB36. We could run both of the parts cooling fans from one plug and from the two existing plugs at 24 volts, and the hard end fan from a different connector. The question would be which one? And this is by the way important. We need to make sure we have all our connectors. We have all our connectors assigned here. So let's assume we use the two fan ports for the parts cooling at 24 volts. Then we have a 3-pin connector for LED. That's cool. We have a 5-pin connector for end stops. That's cool. And we have a 5-pin DuPont connector for the probe. Now let's grab ourselves let's grab ourselves a whiteboard. Let's do this on the whiteboard here. It's going to reflect a bit, so I'm sorry if you can't see all the things, but let's definitely use the whiteboard. Well, it's actually not that bad. And we still have space here. So, okay. We can simplify this by ignoring the motor wiring. That's the first important, I think, realization here, is the top connectors actually don't matter. So let's assume we only have the lower part here. We use one 2-pin connector for the thermistor. So that's done. We also have the green thing here for the heater. And maybe let me zoom you in there a bit more even. And show you a bit more. So thermistor, and I think it's really hard to see, but we have the green thing here. That's our heater. Yeah, that works better. There we go. So thermistor and heater we have assigned. Then we have our two connectors. Those are the parts fan, and we're going to say they are 24 volts. Now we have 5 pins, two 5-pin connectors left and an LED connector. So let's do orange here. The first 5-pin, 1, 2, 3, 4, 5, and I think the yellow will not work, so I'm going to reuse that. Red for 1, 2, 3, 4, 5. And the last thing we're going to do is well, we're going to ignore the LED connector as well. Now, we could run the fans or the parts cooling fan. We could run the parts cooling fan without a MOSFET. Oh no, I'm actually stupid. The fans actually don't run through the MOSFET. The motor runs through the MOSFET, so the fans aren't connected to the MOSFET to begin with. We can, if your motor in any way is damaged, then that's relevant, but not for the fans. Sorry, misspoke there, and we can actually see that in the schematics, I imagine. So the question would be, can we find pins that we can use to control the fans? Okay. Yeah, so this is life. This is life. This is me figuring out what's going on. Interesting. Just so you know what's going on, I am currently checking the schematics. I sadly don't have it set up in a way where I can show you this easily. So okay. Cool. So what we're going to do is we are going to proceed with our fans this way. So we're going to have one fan that is split off. We'll have to solder these wires so we can connect it to one port. And this is going to be the parts fan. And we're going to have the other one go off to our hot end fan. Pretty simple setup. Nothing wrong with that. Fan voltage for the fans will be 24. So this is going to be set to 24 volts or VCC in. So now the question becomes, what else do we have here? We need the LEDs. Those are taken care of by the connector that we have still available here. Up here there's another 3-pin connector for the LEDs. That's fine. Now here's the challenge with those, or the thing we're going to do with these. Usually the way you connect V0 LEDs is you have 2 LED ports. Like the newer Fysetc board has 2 LED ports, which is actually kind of cool because you can just have them addressed separately. The way that the Stealth Burner does it is they have a chain. So every single one of these has a data in and a data out port, and the data out port of the first one gets connected to the data in port of the second one. And with that, you can address them in sequence. Now with the wiring, and this is going to be a bit of a fiddly problem. With the wiring, that means that from one of these sides, at least, you need to run 4 cables instead of just 3 if you want to do that. And we are going to do that to the other side. It's a bit of a pain, but that way you can use one port and you can actually address them in sequence. If you use them in parallel, so if you were to just run, like if you just Y branch the cables for the LEDs, you couldn't. They both would receive that signal at the same time. They would always have the same color. If you put them in sequence, you can have them have different colors. It's kind of cool the way these work. But anyways, yeah, that's something we're going to do for the LEDs. Let's grab our old toolhead board here for reference. We had 2 parts. One, we had the thermistor. One thing that's definitely missing is the pin for our filament sensor. That's something that's easily taken care of. That shouldn't be a big deal. We'll just use probably PA3 for that. So this is going to be the filament sensor. that's PA3. We have PB10 and PB11 for parts and let's use blue. PB11 for these and PB10. Our thermistor is going to be PA3. And our LED is going to be PB0. By the way, if we have ever wondered where this PA, PB stuff stems from, that may actually be something to quickly look into as well, and how you can find out which port you have if you ever work with prototypical components or components that are just not well documented. You can likely always find a schematic, and you can see them here. Those are actually the input banks of this chip. So these numbers stem from the chip itself. So if we were to take the STM32 CAT, let's check if that's the correct one. And we were to pull up a data sheet for those. Paste and go. Let me show you this. Right, I just took the chip, I put it in here. We can easily get a data sheet for it. It actually says that it has CANBus support on board, for example. And well, actually, I might be able to show you this as well. Let me see here. Yeah, there you go. If you look at this, if you look at the pinout, you can actually determine which ports those are by looking at the package that you have. So even if you don't have a schematic, if you can follow the traces on a board design, for example, there we go. Right, and in this case, it's showing the LQFP 100 package. There are other package forms out there. Here's a BGA package. In our case, we I think we have a what is it, 1664 pin package. So the LQFP64 here basically says it has 64 pins, which means that it has roughly 16 per side. Well, actually exactly 16 per side. And then if you have a schematic and you can follow the schematic, you can easily compare it to the package, find out which pin you have there. That can also tell you, in case you're using something special, for example, like CANBus, can also tell you whether those pins are CANBus capable. So if we, for example, check the pin descriptions here, and we want to know which pins are natively CANBus capable, we can check here in the alternate functions column, and it'll tell us which functions are supported. So for example, PA12 is CAN TX and PA11 is CAN RX for this chip, which means that these should be the CANBus pins that are used for this implementation. Let me switch to that real quick. There we go. And I am assuming that if we go in here and we find PA11 and PA12, so that's 32 and 33, it says USB DM, USB DP. Oh, and actually it says B8 and B9. So that is curious. Yes, and it says USB DM and USB DP. So what this basically tells us is that we can have either a USB or a CANBus connection using these. The only other interesting point here is that the actual CAN port is connected via different pins. Which makes me kind of curious to know whether we potentially have the other chip. Let's check that. Whether this was made for the other chip that is also advertised there. And we're gonna paste and go that. That's also a LQFP. Let's grab the data sheet here. And those, let's check here, BGA, that's our LQFP64. And if we look at the pinout here, coming up, we have PA. And by the way, these are ordered in the way they appear on the package, not the way you would potentially count them, which is why you can see here, for example, it ends at PC9 and then it continues at PA. So interestingly enough though, oh, we have USB PD, PM, and with 8 and 9, we don't have any. Now this means that the port being used on this board is not a native CANBus port. That's important to note because it basically means that this board is using CANBus emulation. It is not using the chip internal CANBus, which there may be reasons for, but instead it defines its own. There are pros and cons to that, but in general it's fine, and I think all the boards are doing that. But it is important to note especially if you at some point want to dive into the firmware, then you would need to understand that you need to look for a custom implementation. I'm also not aware of how much of a crossbar configuration support there is in these STM chips, so there may actually be a way of having CANBus on a different port. Oh, PB8, PB9. Is that PB? Oh, yes, yes. Okay, never mind, never mind. I didn't say anything. I retract and assume the opposite. PB8 and PB9 are actually CANBus capable ports. And that would also be how you find out which ports are CANBus capable on chips where the manufacturer actually doesn't advertise it. And by the way, you can actually see here there's a couple more. So PD1, PD2 would be. The question is always, are those actually available on the package? Because if we look at the package here, let's take our QFP16. That's a 64. We have PB, we have PD2, but we may not have all the PDs. Yeah, in this case, only PD 0, 1, and 2 are actually available on this chip. Which means that the CANBus would still be available, but you cannot rely on all the pins in this table to be available on all the chips. So that's a bit of a disconnect there. Anyways, that was quite the tangent here. Let's go back to our browser, and we know our pins. By the way, those tables and the datasheet can help you if you only have like a board layout, or if you have pins that you can trace. You can, for example, go and use a multimeter to probe individual pins of this package and see where they connect and figure out which connections are actually available to you and which pins are which connection. Just by doing that and having the manufacturer's datasheet, you don't even need documentation from, like, let's say the board manufacturer. It's nice to have, but you don't really need it if you know where you get the information from. And that's specifically the manufacturer of the chip on these boards. Pull that up, probe your pins, see what connects to where, and with a bit of luck, you can figure that out. All right, so quite the tangent here. Quite the tangent here. Okay. I guess what we do need to do is we need to splice our two fans together. Whoa. We then also need to, well, this is done. This is done, this works. This is not done. This needs to receive a different connector, but that's not a problem. So we need to depin that. This is done. Okay, one splice, one depin. and the LEDs. That's definitely something we can achieve. Yeah, let's go with that. Let's go with that. I'm going to put our motherboard away here for a moment. And I am going to grab the soldering iron. Now, how do we want to do this? Both of these are quite long. So both of these connections are quite long. What we can do is we can cut one off, cut the other off, just solder those together. We will need to fix those in place though, because we don't want to see the connection move and break. That's somewhat important. And I'm also thinking whether it would be a good idea to reprint this before the outer housing here, before I do anything with the LEDs. I don't think I want to. Yeah, let's go. So this is the shorter one. This is just going to be cut off. I'll probably salvage the connector later. What's too bad is, well actually it's not as big of a problem, because we can still use the single connector to two fans one with the Fysetc board. That's not too much of a problem. Let's go here. Okay. Now this one I'm going to cut off a bit further in, because I want to reuse this part and I want to protect this a bit from the heat of the soldering iron. So having a bit of space there actually helps. The question would be where? Yeah, the location we already had packed here. It's pretty decent. There we go. Split these apart, and these split apart fully. Might not have been the thing to do here, but I guess it's fine. Strip the wires, and I'm going to move that out of the way. That gives us two connectors. and a fan. Two fans and a connector. Finally. Damn, it's late. So there, and so there. And I am going to use a bit of magnification here. No, I actually need to set up the soldering part first. We are going to solder on the top-down camera. I'm going to zoom that out somewhat. Probably need 3. And we wanted to get the soldering iron set up. In case you're wondering, it is a JVC soldering station. And yes, it is nice, but yes, it is also expensive. And no, you don't need one generally if you don't solder day in and day out and you're relying on the best, most consistent quality through all your work. If you're just soldering something now and again, it generally does not make sense for you to be that picky about the consistency of your solder joints. Oh, right. Let's go here until we have that set up. Because a better soldering station and more consistent soldering point joints means over time and with the time you spend on them. So you can still achieve good things with a less expensive soldering station. It might take longer, but if you only do a couple solder joints a year, what the hell does it matter if it takes a couple of seconds longer, maybe a minute or so, maybe you need to do some cleanup for a couple of minutes maybe, then you'll actually, you still save time. I get it, and your time is valuable, but it's about return on investment. And the return on investment for a very expensive soldering station. And by the way, yes, I am going to wear the big one because these wires are so tiny. The return on investment for a very expensive soldering station is probably not worth it for you in the short term, and will take a long time to, I'd say, save you enough time that the purchase was worth it, that you can actually claim the purchase was worth it. So yeah, that's the issue at hand. It needs to save you enough money, as in enough time, to be worth it. And let's say you need let's say you have a very basic soldering station here. You paid $40 for it, and you're now thinking about moving to a higher quality one. You're trying to figure out whether that's worth it. You did about 20 to 30 solder joints per year on the old one, if even. And for those 20 to 30 solder joints, you're now going to be let's assume on average a minute faster per joint. That's 20 to 30 minutes. Now, I'm not sure what you're valuing your time on, but let's take an interesting number. Let's say you're valuing your time after taxes, after everything, because that's actually the money you would pay or you would gain, of $50. That means you if you move to a soldering station that's more professional, that saves you a minute per soldering joint, you just saved $25, but you probably paid $200 more for the device. That doesn't make sense. And that goes for all the tools. That goes basically for all the tools. Let's see if we can. Oh wait, wait, stop. We forgot something. We obviously want to have this heat shrunk, and we want this heat shrunk both individually as well as the whole deal. For the whole deal, we have a larger piece here that we can use. For these smaller ones, we're going to use the blue ones. No, actually, I want to use the white ones. We're going to use the white ones. So there. And this, by the way, is the same calculation that I usually do to decide whether I finally get a label maker to label my cables and other stuff. And it just, you can reach similar quality without one. So the question becomes, what do I save? And yes, I would save about half an hour, so about $25 if I had one, and I could label maker, like shrink wrap label my cables when I do them, for example. Sadly, those label makers are expensive as fuck. There, I said it. And because that's the case, just not worth it. Just not worth it financially. I'm not sure if I ever tried to do a three-prong connection. Don't think I ever did. I'm very curious to see if that works out. Okay, so we have our connection there. The good thing is that these cables are stiff. And that's important, so they don't immediately sag on us. I forgot something. That I just realized because I was smelling the fumes. The question is, where is the anti-fume thing? Oh, and by the way, I can turn you off and get you off the plate. And turn off the trident. There you go. That's what the trident did. It just did it. Slight elephant's foot. Yeah, slight elephant's foot, but otherwise pretty darn decent. Let's shut that off. Let's see if we can find the soldering thing. But I think it's only 2 soldering joints, so it's going to be fine. We're just gonna move on. We have 1 solid connection already, it seems. Yeah, that works. That works, and we now need to get the other set up. Let's just put those down here. And we are going to use the other side here. And you always want to find some way of having those like hold themselves. There we go. It's generally good if they can just do that themselves, so you can basically place the iron on there, heat them up, and don't have to worry that they split apart. And by the way, sorry if you can't see me actually solder. I'm trying to give you a bit of a look here. But it's quite hard to show. And I realize, an idiot. Because I forgot to put the heat shrink on. Which means that we are now in need of deep pinning. Yay. It's especially fun since these connectors are deep pinned so easily. Not. Well, actually, we might not need to. Or let's do it properly. Let's do it properly. I don't want to screw around here. The reason why I'm saying that we may not need to depin is because we could just leave one heat shrinked and then heat shrink the whole thing. That's actually somewhat of a decent idea, to be honest. Let's do it. We don't need to heat shrinks inside. So this is going to be again an excursion into the land of our heat gun. You could do this with a soldering iron, but I don't want to. There we go. That side as well. Oh. Ah. I know where the filter is. Found it. And we're going to cable it from this side. We still need to check the polarity of the connectors anyways, but I don't think it will have an impact on us. Still heat shrinking. Or not. Okay, let's turn that on. And we're just gonna actually heat that up. And I am using 200 degree here, because I think that should be enough to shrink these. And it is low enough so we don't damage the cable or reflow the solder. All right, that's looking good. Okay, there we go. That should be enough. So that takes care of our fan connector problem. I think that can still bake a bit longer though, especially the backside here. Yeah, that's on there now. Cool. Kind of important to do this and do this well, because you do want the heat shrink to support this connection somewhat. So it needs to, it contains, the inside is lined with an adhesive, and that adhesive can actually grab onto the wire and hold those in place. So this becomes a really, really stiff kind of contraption. So yeah, nice. That goes there again. This goes to the other side. And that takes care of our two fans. And getting those connected in any case, whether we use a SHT36 or not. That's off. Why are you not going in there? Dear fan. There we go. I might have mixed up the sides these fan connectors were connected to, so that may result in this little discrepancy. But okay, that this should do. Don't need these then. Okay. We need to also depin our connector here completely, because we need to repin it with another connector. And by the way, I'm going to stand up again. We need to repin that with another connector. Oh, there's the screwdriver. Question is, where is that connector? Probably somewhere in here. Yes. No. didn't I have those connectors out already? I probably threw those into one of these boxes, so that might be the reason here. Yes, I did. We need one of the 5x1s. And we need the... Oh, I'm stupid. I could have actually... (3x1). And we're also going to get the fats out there. And furthermore, we are going to need a jumper. That's what we have now. Let's get these as well. We're only going to need those once we're done with the rest, but I realized just now that we also need to solder some more. So it's a good thing we still have the solder equipment out. So this is next. Let's put this aside for now. There's our repinning pin, and now since these are smallish, let's do this with the vise. Put that on there. That in here. Actually, I think the other, the other bit might be the better one for this. There we go. think I like the pH ones better than the XH connectors for JST. They're easier to depin. They're actually easier than I thought to depin as well. Okay, so let's move to our documentation here. And let's look at the pins. We decided to use the all the way right pin to do our end stop connection. So that's PA2, and this supports 5 volt and 12 volt plus ground. The documentation here suggests PA2 and ground. So we are supposed to do the we're supposed to wire this in a way where we have the second pin from the left and all the pin all the way to the right connected. In this specific case, it doesn't even matter whether you connect or like we do have a black and a yellow wire here, if you can see that. But and by the way, I didn't actually want to use that. I wanted to use the smaller one. Because there is no actual ground. It's a switch. It's a switch. Either the current is flowing or it's not. That's the only thing you need to know. It's the only thing it does. Okay, that's in there. That's also in there. No, they're both not. What the hell? Okay, it seems like we damaged our connector a bit while depinning. These have small tabs on them. And if you press these tabs down too far, they will not hook into the tabs on the connector anymore. Which is a bit of a problem. Yes, I need the other glasses for that to see that better because they are so damn small. And these really tiny tabs are basically what's preventing your connector from sliding out at all. So you want them to be properly in place. You need them to be properly in place, otherwise your sensor is not going to be reliable. And for a filament sensor, that might not be a good thing, because you usually have your printer set up to pause once you're noticing a filament problem. So yeah. That should actually be good. Yes, these were kind of flattened. So pulling them up slightly does help them stay in place better. And I guess we didn't do enough here. There might also be a concern about the connectors actually being compatible with these. But I do not want to recrimp them. Recrimping them would actually suck. What we could do though, here's a thought, is these are, I think, compatible with the ones we got from the crimping tool. Oh wait, we have those there already. So we could just use those instead. Almost identical. Second one from the left. And all the way to the right. Yeah, all right, cool. That one's still too loose. I don't like that. And sorry, by the way, I can't actually show you this really well. But yeah, it is important that these stay in place because especially if our printer goes really, really fast. We need these to be reliable. We need these to not shake out of the printer. there, that formed a really massive hook now. So as soon as I get that seated, that should probably stay in there pretty well. All right, cool. That is actually in there. Nice. Nice. So that gives us our connector here. That gives us our connector. That connects there. That connects here. The other fan connects there. Thermistor there. This we don't need. This is going to be our hot end. Since the thermistor is going on this side as well, I'm going to flip that over on the hot end. And that's the wrong one. Where's the right one? Where's the correct? Where's my screwdriver? Damn it. Oh, there we go. There it is. So we're going to swap over the thermistor to the... No, actually we're... No, actually we're not. The thermistor wire is considerably longer than the wire here, so that's fine. We can just route it on the other side. But also, if you look at this, this is kind of formed. Having that form on one side, I don't want to move it to the other side. Cool. So that solves that problem really quickly without us having to do anything. Next, jumper. The jumper. We have ground PA1, PA2. We want that connected with VCC. There we go, so that connects VCC. Let's put some connectors on the board here. Oh, fuck. No. No, you bastards. All right, all right. That one I really would have liked to not have to do. So the reason why I complained just now is because while all the other connectors are using a GST PH connector, the motor uses a GST SH connector. Somebody needs to riddle me that. I don't get it. What the hell's going on? The reason why that's important is because it means that we need to... Oh, actually, we're not going to put in the hot end. Or do we? No, we're not going to put in the hot end just yet, because we're going to do the LEDs first. So this is LED 2. We don't do that one yet. We need to first desolder the blue wire from this because the blue wire is damaged. Then we need to find a file that is really small, or we need to use a knife to clean up our interface here slightly. Make that slightly larger. Actually, let's do that first. That also while we do that, this can also take a bit of the edge off here. There we go. That should now be way more smooth. Just take some of the edges off. And while we did that, our soldering iron is up to temperature, which means that we can desolder this now. For desoldering this, we have two problems here. The first one is that there's actual solder there. So we need a desoldering gun and potentially a wick as well. There's wick, and we're just going to try and find a suitable solder sucker. Because I don't remember where that is. It's a bit messy. There we go. That's going to do. So if you want to desolder something quickly and you don't mind the mess as much, like we do just now, or now, you can just take this, hold it on your solder joint, in this case with the cable attached, you can just pull on the cable and wait for that to come out. But that only works because it's only one pin. And it might not even, depending on how you shape the cable on the other end. But there you go. That's off. Now, what we need to do now is we need to get the remaining solder out. For that, or at least as much as possible, because we want to resolder this. So we're going to put the iron on the opposite side. We cocked our soldering gun and we're basically reflowing this from the other side, waiting till that flows, then use the sucker to, wow, suck out all the tin. And what you're left with is a more or less virgin solder pad and a soldering iron that's on the table. So maybe not the best idea. All right, so now we need another wire that is somewhere here. Gonna use blue. And we're gonna cut that to size. Strip that. Twist it and put it back in. Now I'm going to need the glasses again. You want to make sure to put all the strands of the wire in. With these really small ones that are meant for the V0, that's actually not as easy as it sounds, especially with the what is it, I think 22 gauge wire I have here, but it is possible. You just need to tightly Okay, so where's the cable? There's the cable. Yeah, it looks like my audio cut out there for a couple of minutes. Don't think it was all that bad, but yeah, here we go. Here we are again. I was just saying that I really don't like how the LEDs are done on the V0 and Mini Stealth Burner. There must be a better way of doing this. There must be. Yeah, let's do it like that. We're gonna clip those in again. Looks like we missed one single strand. So, gonna do the unthinkable. Just cut that off. And then clip that in. Solder that back on. Damn, this took longer than expected. All right. Actually, I want to check my work here. Think it's good, but trust but verify, even yourself. Yeah, that's fine. So now the actual challenge is to get 4 wires to pass through there, especially these thick ones. It's not going to be fun. It's going to take a while. The first thing we need to do is we need to decide on a direction. And we need to decide on a side. In general, I think it's better to pass in the short side first and then funnel the long side. By the way, the short side and the long side, I'm saying the LEDs are going to sit in front of this, not in this. They can't sit in this. There's just no room. That's what I mean with I don't like this design. Is they're basically sitting in the front, and I can probably show you images of that as well, just so you know what we're going to do here. Go to the browser. You see how these sit in front of the let's see if we can get a bigger picture here. In front of the actual print. So they're basically held in there by the cable and probably a bit of hot glue. That's all. Well, actually, I'm not even sure I would use hot glue there. some normal glue, I think. With some of the vendors, you actually get a bit of a description on how to mount these, but not all of them. But yeah, we need to get those cables through. And what I mean, again, with the long side versus the short side, going to move back to this, is the long side is where the cable moves the long way inside here, the short side where the short side is basically going to go through first, then the long side afterwards. The short side we want to push down when we funnel the cables out, and the long side we are going to have come up on the top. By the way, on this turned around tool head. So I think we can safely take two cables, just funnel them through. And we're going to use this side here. There we go, two cables through. Now long side with blue and red. These are going to be tricky, at least for this type of cable. I suggest you use something smaller cables like AWG or gauge 24 instead of 22 like me, because you're going to have an easier time getting your cables fed through. Again, these are the only cables I have at the moment, so I don't have an alternative. But it is a bit of a pain. Even the third cable seems to be a bit of a pain already. So maybe let's try doing it the other way around. Let's push the long side through first, and so there, and then let's take the very short side after. We can also use our pin to maneuver those cables around a bit. And that's number 3. That actually went through reasonably quickly as well. And now for number 4. In general, if you're building a new printer and you're doing this, By the way, the Fysetc, the new Fysetc kit actually has this wiring harness included, so you don't have to deal with this. But this kit, the old kit doesn't, so you have to do these things yourself. I just realized, let me zoom this out a bit so you can see a bit more. Need some magnification on that. And more importantly, some light. Yeah, and I think the most important thing here is use a smaller wire gauge than me. Or like smaller wire diameter, rather. That is true as well. It barely fits. And by the way, the reason why this has 4 wires and not 3 again is because I decided to wire these in, wire the LEDs in series. So we actually have one of the wires going from this LED to the other. And I like the fact that this time, when I'm pulling the cables, they're not actually stripping. Which was why the other cable was stripped last time. There was a sharp corner in there that just tended to strip the wire. Shit you don't want to deal with. Using PTFE wire might have not been the best idea to now pull this through. The good thing about the wire we are using here, and that it is so thick, is that it is also going to hold this in place really well. So we don't even need any adhesive right now. We can deal with adhesive application later. The interesting thing that's happening now though is one of the wires on the short side is bunched up, so that's going to be a bit of an issue. Also, I was somewhat stupid in that I should have checked which wires were D in and which were D out now before. And there we go. That should do it. Now to find out what's the in and the out and all this stuff, we can simply do that by looking at the labels that are super. Actually, the labels are on the back side, so that sucks. But we have a ground wire visible on one side. Ah, shit, and I realize why. Why we are having the issue of the cables bunching up right now. That sucks. Yeah, that needs to come out again. Damn it. The reason why we're having an issue with the cables bunching up right here is because the yellow wire is wrapped around the black wire, and that is obviously not something we want. What we can do now is we can push the black wire inwards a bit. And that solves the problem, because there is space in between there, so yeah, that should be fine. It's actually sitting really well. Now again, we have a VCC and a ground wire, and to find out which color we used for the out, whether that was blue or yellow, we can look at which side here on the one we haven't mounted yet corresponds to the side that the D out is on, and that should give us a good idea of what we need to connect next. So, looking at this, we have the in with the ground wire and the out with the VCC wire, which means that VCC is bunched up with blue, so blue is our out wire. The way we now need to cable this, and this is a bit tricky, just so you're aware, is we actually need to feed the out wire through this as a D in, and then we need to solder this to the other one. That's the reason why we only had the other ones connected preliminary, and this also provides us with a bit of a challenge of measuring the length, because we don't want this to flap around in the breeze, but at the same time we want it to be long enough to do maintenance on. The assumption being that if we firmly tuck that in, like the same way we tuck in our other wires, like here and here, and if we then have that run in a bit of a loop, we can still get away with having our connector somewhere here, So we are going to pull this through all the way. Then we're going to make a cut here. And if you now look at the wire length, that's pretty comfortable. That should be fine. But we can also, now that the wire is running freely, we can pull that all the way through. And we can strip that. That did not actually strip. Let's cut that off some more. Well, actually, it's one side that didn't strip. Don't like that. We need that to strip cleanly, because otherwise it won't feed through well. The problem with the stripping here, though, is that we're stripping very short. And by the way, let me also put that on. No, later. And we need to now get that attached to the other side. Again, need to use some higher magnification here to make sure that all the strands go in well. And we want to wire this to the in. That's a bit too short, so let's cut that off again. Strip some more. And the end is on the ground side. That fit through beautifully without any resistance. That's actually what you want, because that means that all your strands are aligned and sitting in there well. And this wire gauge is just about big enough to fit through there. Soldering iron is up to temperature. Nice. Actually, want to check that we are not leaving any strands behind. Nope. That looks really good. That looks really, really good. So now that we have one wire through here already, we need to pass the other ones through as well. This shouldn't be as much of a problem since we are only dealing with 3 instead of 4. But it is still going to be really tight. And I actually didn't remove as much material from this side as I did from the other. So it's going to be a bit tighter than the other ones. one all the way to the top. Making sure that I'm not stabbing myself. And this is, by the way, the second time I'm doing this. I already did this for the salad fork, and it wasn't much fun there either. But if you only have one LED pin, or if you want to actually have the option of addressing all your LEDs in one chain, then this is the way. To be honest, I do like the Fysetc solution though. Because it removes this complexity. It removes this complexity of wiring, especially. Other toolhead boards like the SHT36 on the salad fork, this is going to be really fun because the salad fork is going to use clicky, and because it's going to use clicky, we have the problem oh, and it's not just going to use clicky, but it's going to use clicky and an end stop and a bunch of other things. So we actually do have the problem. Damn it. That we're running out of pins on that one. By the way, in case you're watching this, I'm a bit disappointed that you're not here, because I was kind of hoping that I would have you here for this part, so you can tell me whether I'm doing this correctly or not, because I always feel like I'm doing things in a stupid way here, and that this cannot possibly be the best way of doing it. But if you're not here, and you cannot tell me how stupid I am, I'm left to my own devices, and that usually isn't good. That's not good. You need to be here. You really need to be here. So, if you want to be here, Saturdays, usually 7 p.m, depending on the weather, maybe 8 p.m. It kind of depends, because I do have a dog, and that dog has needs, and those needs are best met outside in the sun while it is still sunny. So sometimes 7, sometimes 8, we're going to have this. The other one, that one. That's Central Europe time. If you're in the UK, 6 or 7. If you're in the US, East Coast, you will find us 1 to 2 p.m. ish. Or if you're on the US West Coast, 9 to 10 a.m. ish, obviously. And I should really have used smaller gauge wire here. There we go. That's in there. Now we can pull these through. Making sure not to pull where things are not moving, because if you do that, you're going to end up stripping your cable in the middle. And you're really not going to enjoy that. Especially if you're this far. Having to take this all apart right now would suck so bad. And look how well that went into place. So yeah, LEDs. Now we still have one more challenge here. We need to connect this. We need to cut these. I think we're going to leave those a bit longer. So assuming they run off the side here, run off the side there, then I think it's safe to cut them somewhere here, get them connected together and then to the actual connector. That's what we're going to do. Snip. And this one as well. Snip. And this basically leaves us with these these 5 cables to connect. Red and red, black and black. Red and black both get an extension from the cable that we just cut off. Yellow is does its own thing. Yellow is data in for the LEDs. So, good thing we still have heat shrink here, because we're going to preload that on these. That keeps those together as well. And preload that on these to keep those together. Strip these. Damn it. Don't think that's stripped well. Let me see if that's enough. No, I want to take off more. Yeah, that's okay. That's fine. I'm trying to basically strip about 5 millimeters. Usually a bit less, sometimes only 3. Gonna strip some off here as well. If you strip too little, at least these strippers tend to not do a good job. They need something to hold on to. They cut, but they also then drag, and if they don't have something to hold on to, they're not going to do a good job. I'm not sure if that's the case with all of the wire strippers out there, but these definitely, they're cheap. They're cheap though. So same deal as last time with our connection here. We're going to pinch them together. Then the other side. Try to really get those, really get those individual strands to mesh, so they hold each other in all directions. And that's going to give us a good connection. There you go. And that actually was not a good idea, because one of our cables deserted. There we go. Now we're just gonna heat that up. Get some good heat into this. And slowly apply the solder. Let's check that. Yeah, that's solid. That is good. Same deal with the other side. Get these twisted together. Clamp them in there. Get ourselves a cable on the other side. Really mash those together. Heat it up. check our work. Nice. And of course, now we need our heat gun again. Good thing that's still out. So there. That's now confirming to the connection. It's going to help it stay in place. This a bit more there so you can see a bit more. Let's finish this. And obviously you don't want to hold this in one place. You also want to do this steadily until you see adhesive coming out the end. Because again, these are lined with adhesive on the inside, and the adhesive helps these stay in place and helps remove the strain from the connection. You can get this started really quickly on one side, but you want to move around to all the sides, all the other sides as well, to have this evenly shrink and grab onto the wire, and not one side at some point overheat and potentially damage your heat shrink. And I realized that you cannot see all that much. And I know I could set the temperature higher and get this done faster, but I'm usually erring on the side of caution. If I can do it slow and steady, make sure I don't need to do it again twice, that's good enough for me. also going to do a combined heat shrink because it just helps stabilize things a bit more. So there, that's the new wiring, almost done. A bit more crimping, but that's it. Yeah. All of this hassle, by the way, is done for you on the newer kit. I know I already said that, but I'm not sure you realize just how much that means in terms of Fysetc taking away build time from you and build excitement from you. No, I'm kidding. I'm kidding. If you're just looking to build a printer and you want to have a CANBus toolhead, sure, the new kit definitely has you covered. If you want the LEDs, the new toolhead board has you covered. There's a bunch of problems. Maker Milo confirmed that are not present in the new kit anymore. So yeah, but let's assume just about this much. Let's strip these to, in this case it's GST pH, so 3 millimeters. That was one good strip. Let's get these sorted. What I'm really not liking is the requirement for me to re-crimp our motor here. I'm actually considering using another motor. Now, using another motor has other implications. We don't necessarily would need to redo the extruder here. Well, think about it, think about it, think about it. Because the downside of using another motor in this case would be that actually let me see something here. If we recrimp this, basically the problem is, and by the way, this is absolutely bonkers because so the EBB36 actually uses XH JSTs. Interesting. That is wild. That is wild. Anyways, let's get through this here real quick. Which one do we need here? I think we're good with 3. I think we're good with 3 for the wire thickness. It says 24 to 20. So yeah. I need to watch my video on how I crimped these last time again, because I know this was easy. I know this was very easy, but for some reason my hands are not willing today. I can't get the freaking crimper loaded. Oh, okay. Okay. There we go. That should do it, and now we can push our cable in, crimp that down. That looks just about perfect. That's also perfect. I mean, these crimpers are dirt cheap. Dirt cheap. And I just realized that you couldn't actually see what I was doing. So here that actually still needs to be stripped. So let's take off 3mm here. There we go. And then I basically preloaded this with the trim piece. And I am just pushing in the cable until I think the cable housing is far enough in. And once the cable housing is far enough in, I push them together. So nothing much to do there. The connectors, let's see here. This is still the website about the, this we also don't need. This is what we wanted. LEDs, LEDs, LEDs. Where are the LEDs? So it's ground on the right, signal in the middle, 5V on the left. Since we're oriented this way, that means we have the pins there, ground on the right, 5V on the left. Let's put in 5V first. Also, let me see. Oh, don't tell me those are the wrong ones. Don't tell me those are the wrong connectors. Let me see here. Ah, damn it. Yeah, that makes sense. That's also why they felt different in crimping. Because those connectors that we just crimped are XH. So let's do it again. And right, they would need to include XH as well, because they basically require you to recrimp your, in some cases recrimp your existing kit motor. Yeah, that feels right. Yep, that looks good. This is too long, so we're gonna cut off a bunch. Yeah, that's kind of what I thought. Make sure to push these in far enough so they actually grab with the sheath, with the cable housing. Otherwise they will be relatively easy to pull out. Also make sure that they don't only grab the cable housing, because then you have a non-working connection. And obviously that is no fun either. So we're going to push this in as a the last one. That should be fine. Now, again, from the top, 3-pin connector. We need to put this in this way. Actually, we can go to the overhead here. Zoom in some. Connector this way around. The ground is meant to be on the right side. And the thick end needs to go down, so that's the correct orientation here. We can finish pushing them in once they're all seated somewhat. The red one goes there, and the yellow one is actually the shortest one. That's actually rather short. Okay, interesting. That's not going to be good. That is not going to be good, but we'll make it work. But it is short. It is very, very short compared to the others. Should have probably left that longer. It's actually not surprising that that's shorter, because we cut all of them to the same length and then tacked on a bunch on the power wires, but obviously didn't do so on the signal. So I'm thinking it's still going to be fine, because we originally measured without the tack on part and already had that packed us to as long enough. But yeah, now we need to get those in there. And that doesn't seem to be all that easy. Because of the thick wire, basically. They are not going to go in easy. So yes, if you're doing this, use thinner wire. Okay, that's in there. And you want these obviously to be fully seated, so the little paws grip properly. Yeah, that's going to be one solid connection at least. Okay, so those are going to be our LED wires. Now we can also, for test, put in our hot end. Since we have the LEDs in place now, nothing keeping us back. Put those hot-end wires in here. And I am very glad that we decided to use proper ferrules here. There we go. We'll also have a thermistor wire coming from the other side. That's going to go under everything. Ah, damn it, you're actually not seeing it. Thermistor wire going under everything. And then up in there. And now the only thing that's really left is the motor. What do we do about the motor? I think we're going to well, let me see something here. If we're assuming the motor is here, this is pretty relaxed. We can still get away with a bunch less before we run into issues here. So push comes to shove, we can recrimp that to the smaller standard. Otherwise, we just saw the EBB36 also uses the larger standard, so let's just go with this. Now, yeah, the way we're going to do this is we're just going to hack these off. I'm not going to reuse that connector. There we go. Blue, red, green, black. And we have it here, blue, red, green, black. This, by the way, being a bit of an experiment or like a bit of a gamble here. That's also why I would leave the colors in the connectors, because that way you still have the pairings. You can basically assume that the pairings of your wires are adjacent to each other. So blue and red will be paired and green and black will be paired. And that's how we need to recrimp them in the with the larger connectors as well. So yeah, that's the goal here. There we go. That last one didn't want to go directly. So now we need the XH sized connectors. So let's grab ourselves the connector here. And obviously we spent 3 of the 4 other connectors that we actually got, so not a fan of that. Please, oh please, dear mellow, include more of your XH connectors. By the way, one thing I really like about this kit, the other XH only crimping kit did not come with clipped off connectors. I really like this. The fiddling around with those is not my favorite pastime. There we go, that's number one. And same deal. Push in until you think it grabs the sheath, and then close. Yeah, what else can we talk about? I've been enjoying Forza Horizon on the Legion Go tablet. That's quite fun. That cost me more time than I imagined it would, to be honest. Ooh, and this is interesting. So blue and green have copper wires, the copper colored wires, while the blue and black do not. So there's even some marking of direction, I think, applied here. I'm not sure if that's the case with all steppers, but this one definitely. Wow, that's really close. The green, I can see the sheath. The red, I can see the sheath. The blue is really, really close. Okay. Okay, that's weird, but we'll make it work. And by the way, I am not sure who designed these crimping pliers, but loading them is a freaking pain in the ass because they're not opening wide enough. Oh, 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 oh. That does not look good. Black does not look good. Nope. Black is too wide in there too deeply. So we'll need to do that again. The problem is if you push the wire in too deep, that results in the connection not being good, because your crimped connector will only make contact with the sheath and not the actual wire. So you'd still have contact in many situations because the wire then gets bunched up in the front of the connector, but it's not a as good a connection as you would have if your inner poles would directly bite into the Where are you? There you go. Your inner poles biting directly into the wire basically gives you a better connection. Or directly pressing into them than if you only have your that's better. There you go. Now reference. Let's try this first. Black, green, blue, red. Are you kidding me? So black wants to be a problem child. While we crimped that, I must have had the connector at an angle, resulting in the pawl that's supposed to keep the connector in there to be flattened, and now it doesn't grip anymore, and there it was in there so good that I couldn't see a way of actually getting it out. But no matter, we'll get there, we'll get there. And by the way, please realize, if you ever see this, me doing this means you can. I am really bad at anything constructive or physical in nature. Yeah, that's good. So if you're wondering whether you can actually make this happen, if you were to get a kit, any kit that is, or let's start with Vorons. I think there's actually Black, now green. Very little chance you would be doing worse than me. And I think we got blue as well. Blue needs to be redone. Yeah, that basically fell off. That's never a good sign. All right. And this stream again is way longer than I thought. But at least we got something done. At least we got something done. There we go. Turning that around and fitting it. Nice. Okay, so challenge now is going to be this needs to go under here. Then we're gonna have our EBB36 sitting there. So I guess we can already screw these back in. That's cool. And we will need some additional, I imagine, M3x6s or M3x8s. Not there. See here. Yeah, M3x8s are just fine. So we're going to use those to mount our EBB30, well, no, SHT36, please, in place. And then we're wrangling the cables afterwards. The aim was off. There, that's on there. It's not even coming out the other end, so pretty good, pretty good. I like the fact that this solution actually uses a plastic part. That's also on color to do the connection between the upper and lower part. Now we do have a constrained wire here. I really don't like this. Yeah, that is shit. Now, I told you earlier, you can see my problem here is this black wire. That black wire is just stretched. And it is stretched because it is now going all the way to the other side. And we had some issues with it previously that already made it shorter. The trick is going to be, because we know that we have more wire on the yellow, the trick I think is going to be switching the yellow and the black wire. That's not going to be very intuitive from a hey, this is ground, this is the signal point of view. But since this only connects to a switch, it really does not matter. I'm going to have to remove this first. Now I can pull out this. So we should be able to change these. Obviously we made sure that they are seated properly earlier, so they're not going to come out as easily as before. But this is why I didn't want to remove and recrimp these connectors. Then the cables would have been even shorter, and that wouldn't have been any good. So let's see what happens if we switch these around. I think we can also still improve on the grip the yellow cable has, the yellow wire has, at least a bit. And by the way, I think we're also going to still at some point add end stops here. Sensorless seems to work for this at the moment. But I do trust end stops more. Okay. Now the ideal path would be over, but we're definitely not going to make that. Whew. The problem going under and between is that I'm not sure that path is available. But yeah, this is a way less stressed connection now. You can see it here. The connection is way more relaxed. Both connectors are seated, I think. Yeah. It's pretty good. So we're going to leave it at that. Bit of a compromise, just something to realize that this is not optimal, but it had to be done this way. That means we can go under here and connect this again. And that is basically it. Some cable ties. That tie all the things to their respective side. And we're good. Ooh, and my headset is running out of energy. That is usually the cutoff. So we're still going to put that in the printer, but once we're done with that, that's it. I'm going to call it. Now this time I need to be more careful with which direction I put the cable ties in. I don't want them to sit on the outside. I want them to sit flush. So I think they need to go in with the entry on the top, and then pulling the entry up. So that would be this way, and then I can have the lock sit neatly on the inside. Hopefully that doesn't interfere with anything. Okay, that was one. The second one on the other side. It's going to be a bit of a bigger loop. Again, lock on the top. And just going to get it started. The only thing we're not going to cable tie this time is the actual sensor there. No need. There is no need for that. Okay. That is in there as well. Those need to stay out of the way. We have a couple of cables that are a bit tight, but I guess it's fine. 1, 2, 3, 4. Let's put it back in the printer. We're going to deal with connecting it up next time. Ooh. Yeah, that's better. The LEDs do interfere somewhat with the sock. So that's not going to be fun when I have to put that in. Yeah, but with a bit of care, the sock sits well as well. So this bit of chaos here is going to be our printer. We need to get these cables out of the way a bit, dispersed a bit more, but otherwise I think we can make this happen. Let's see if we can put that in, and once that's in, that's going to be it for today. Whoops. I actually don't want sound there. You're the only ones with sound here. Let's get ourselves some space. let's get our little printer. It's cold by now. So, top head open. And here's our massively improved toolhead. Well, I don't know about massively improved, but it is a toolhead. The cable mess is a bit of a problem though. And I think a bunch of those cables could have been a bit longer, to be honest. We'll figure it out. To set this in place, I'm going to use the big screws through the front first. That kind of helps push things into position. It's a bit hard to see though where position is. There we go. That is sitting very well. Now the second long one is there. And now we need to fit the plastic part. That's loose. Yeah, remember our yellow wire? That yellow wire is not doing well. Everything else is fine. But that yellow wire really is too short. That is a problem. That is not going to be easy to fix. I think we can still get away with it. Just let this settle. But it is definitely something to look out for problems. Okay, so that's on there. Now 3 screws left. No, 2 screws left. We need to somehow access the bottom ones. Oh no, and we actually need to loosen that again. And fold our board here up again. Because there is another screw that we left in the carriage. That also needs to still be properly connected and properly screwed in. So pull that up again. And then find our way through the frickin' cables somehow to our little screw. And here is where I like the lighting on the glasses, if I can find the frickin' there things, because it is just too dark under there to really see something. Also, I think somebody had a really good idea when they designed this back cover, because they left a cutout for actually reaching this screw on purpose. So I think you only need to take off 2 screws now instead of 3 to reach your tool head, disconnect your tool head. So there. Now we have 2 more, one there and one the other side. And then we're done. Whoops, deserter. What? That is not a good thing to do. Don't do that at home, kids. Going to do that one first. So one thing I am immediately noticing here though is that the Fysetc standoffs to the carriage and the width of the carriage don't seem to fit. And I think they never did, because did that screw actually go in to the bottom? There we go. That sounds weird. So there are screws loose. Need to look into that. Need to check where that is. There we go. That might be it. how can I best reach that? Because while people thought of a way to get your printer out with only 2 screws, they did not realize that the SHT36 put the hot end mount, the hot end connector that usually connects to downwards directly over the screw. No, no, this sucks. They should have thought of that. They really should have thought of that. Oh shit. I don't like that. I don't like that at all. So while we did gain some advantages, or did they? Maybe we can carefully get in there. Nope. That is exactly where you don't want it to be. I may need a larger glasses, not for the magnification, but for the light. Yeah, so that sucks. I suggest, therefore, placing the screw first before you... Well, actually, I suggest placing the board on the carrier before placing the... before doing the connections. And then once you're doing the connections, already having the screws in, and leaving the screws in, just loosening them. Because you can get a screwdriver past the hot end connection, but you cannot get the screw past it easily. You can, but not easily. Lots of light helps, as we saw just now. Although I'm not sure if I now cross-threaded the damn thing. Okay, that is that. And what we're also going to do, since we're not going to run this printer until the next session, is we are going to put in the cable already. Taking that apart is going to be a bitch. I'm going to put in the cable here. And going to connect that. Going to connect that back up. And then we can already size our cable here. One of the advantages, I think, no, damn. Okay, that's actually even worth mentioning as a problem with this approach or with this solution. That is definitely going to rub all the time on the top of the printer. Because this connector is so high and because this top lid is like, I don't know, I don't like it. I don't like it. Let's move that down somewhat. And let's actually close this up so we can test it, so we can see. And you, as always, cannot see anything because the printer's in the wrong spot. There we go. Let's close this up. And I think we have another problem here. In that our cables need to be bound higher. Because they otherwise interfere with our end stop, because this board puts the connection so low. Wow, all of this stuff. I mean, come on. Yeah, we need to pull our cables higher. We really need to pull our cables higher. And these are going to sag and then interfere with sensorless homing. So this is not good. The blue cable is a problem because that runs directly under the carriage. So blue may need to run inside. That's not a big deal. Blue can run inside. That's something we can do. But we also need to use a cable tie to keep these cables from sagging. Cool. We'll deal with that next time. For today, I gotta tell you, I am pooped, and I also don't want to do these changes and want to fix those cables in place until I've tested the printer. So for the moment, let's conclude at that. So we got our toolhead board installed. The installation isn't as easy and seamless as you'd think. We noticed that we can't actually assign two different voltages, different fan voltages. That's going to impact us in, at least somewhat. But otherwise, we seem to be mostly good. Yeah, so that's basically it. The fan voltage is the worst disappointment. We may also need to do something about our filament sensor wiring. That may be too short. The LED wiring may also be too short. It's not as bad. I think the LED wiring is fine. The toolhead wiring at the moment has slack, but it's not. I don't like things to be this tight, because it if things are this tight, they usually cause trouble, cause stress points at some point in time, and those stress points result in unreliable behavior. But so far, otherwise, we're doing pretty well, I'd say. We're doing pretty well. There's not too much I'm concerned about at the moment from that solution. Let me know what you think. If you see this, if you like it, drop me a like. Share this if you think it's shareable. Yeah. Drop me a dislike if you don't like it. Leave me a comment. Maybe join next time. And let's see what else we can do here. And in the meantime, enjoy your weekend. Get yourself a printer kit if you are so inclined. Have some fun yourself, do some experiments yourself, and as always, thanks for playing.